Alright, so this time the story isn't about beer, but it's about agriculture, because that's where ANOVAs originally came from. So anyway, another little Jeopardy fact for you. So there's a lot more to it than that. That was actually not the direct ANOVA that came from agriculture, but it's kind of its preceding tool, if you will, and that eventually developed into that. So let's move forward and start talking about what ANOVAs are and how we can use them, and we'll hopefully answer some questions that were in the book. All right, first off, we're going to use ANOVAs to compare multiple means. Remember, t-test is just one pair of means. We have one mean now, compare it to another mean, and so on and so forth. So if we have multiple means, like 3 different conditions, so you've got a control condition, a level 1 experimental condition, a level 2 experimental condition, you could use multiple t-tests between condition, for crying out loud, my phone will not stop today. Anyway, we could use a t-test between condition A and condition B, and condition B and between condition C, and between condition A and condition B, between condition A and condition C, but that creates something called family-wise error. So let's look at family-wise error. Basically, it's just an increased chance of making a type 1 error, right? So if our alpha level for a given experiment is set at 0.05, that means we have a 95% chance of not making a type 1 error. That's for one experimental test, right? So, and it assumes independence of tests. But if we have more than one, let's see what happens. So in that situation, I just described 3 conditions. So we would need a comparison between condition A and B, between B and C, and between A and C, right? So we have a 95% chance of not making type 1 on the first one, 95% on the second, 95% on the third. And this is a multiplicative function. So we have a total of 86% chance of not making a type 1 error if we run 3 t-tests on the same data set. In other words, we have a 14% chance of making a type 1. Remember, we started out with a 5% chance, so now we're basically creating the chance of screwing things up all the time. As a result, we should not use t-tests. There are other things we can do. There's something called a Bonferroni correction, and we'll address that later, but it's just not a good idea to use t-tests. We have a tool called an ANOVA that deals with it directly. So let's take a look at how we can use that ANOVA. All right, ANOVA simply means analysis of variance. Right? It's basically an acronym. So it's not ANOVA here, analysis of variance ANOVA, that's not it. It's just ANOVA. So we're going to use ANOVA when we have more than 2 groups, right, that are made up of different people, and you're comparing scores between those groups. So we have the independent stuff here, right? There's other types of ANOVAs that we can use when it's the same people, like a repeated measures ANOVA, just like the repeated measures t-test, or the dependent samples t-test, but we're just going to cover this basic ANOVA and a factorial ANOVA. So I think your book, excuse me, big yawn. So I think your book calls the ANOVA, the simple ANOVA, a one-way simple ANOVA, and that's a great way to talk about it. And we have this one factor, right? So we're going to have a one-way simple ANOVA is really just a basic ANOVA. There's like 10 different names for it. Anyway, it's a single factor ANOVA, however you want to look at it. So one factor that we're going to look at, in other words, a treatment variable, but we have more than 2 groups in that factor. For example, let's stick with our t-test example with the smoking stuff, right? So smoking cessation program, so we have 3 different things: the patch, the pill, the gum, and that's just 3. We could add a 4th, a control group with like what would you call it, cold turkey, right? Or no desire to quit, whatever. So you could have 4 levels, right? So here's 3 groups that we have. We could do that t-test thing, but we run into the family-wise error because we would have to compare patch to pill, pill to gum, and patch to gum. So we're just going to use an ANOVA and compare everything all at once, right? And it spits out one result, and then we go from there. Okay, so let's look at the logic of this thing. The logic is really straightforward. We're going to take the model and divide it by error, and that's going to equal our f-test. This is what we've seen repeatedly. Okay, this is the same thing we talked about in the past, where we look at that between groups variance divided by within groups variance. In other words, what we think the differences are between groups, i.e. the model, divided by the error, i.e. the within group steps, and that gives us our f, right? So our f is the Fisher statistic, so Fisher's f-test, which is an ANOVA, right? So as the name suggests, we're going to be comparing variances here, and that's what we're going to be focusing on. So we're going to kind of skip over all of the details about how do we get to those individual calculations and where does all that stuff come from, and we'll look at it a kind of a superficial level because there's really no need to go into all those crazy details, but I do have to get into some detail here so it makes some types of sense. So again, we've got the variance within groups and the variance between groups, right? So that, and we're going to take the variance between groups. So in this case, we have three different sources of three different groups that we have to look at the between factors of, right? So the between the groups from A and B, between groups B and C, and between groups A and C. So we've got to calculate the variance, the proportion of variance within each one of those groups compared to the total variance, right? And we do that. Your book goes over a little bit about how that's done, but it's basically by taking the overall variance in the entire data set, and then calculating the variance within each one of those different categories or groups, and then getting some ratios and going from there and doing some calculations based on that. Right? So again, we're going to take the variance between groups. That's the stuff that we're interested in. That would be the effect of the pill, the patch, or the gum. And then we're going to look at the variance within those groups. That's going to go in our denominator, and that's going to be the differences in effectiveness for the pill for all the people in that category, the differences in effectiveness for gum for everybody in that category, and the differences in effectiveness for the patch. Right? So ultimately, we'll divide that between groups variance by the within groups variance. And then essentially it's really an error term, not just the within groups variance, but there's an error term in there, and we'll divide that so it starts out with the model divided by error. Simplify that out, it becomes between groups variance divided by within groups variance. That's going to give us our SF value. In other words, that is basically our corrected model, if you will. That's we're going to be able to say that yes, this is significant or not, using those same criteria that we used before with the t-test by looking up things looking up critical values based on degrees of freedom. So we're going to have to go through all that stuff, right? To be 100% truthful, though, we don't just stick with the variances. We actually switch down into the mean squares, right? So mean square error, right, is what we're going to try and remove from or use in our formula, right? So we know that total variance is from all points, and by all points I simply mean the total variance for the entire thing, right? So just ignoring all groups, there you'll get a variance there with all those scores. You get the variances for group 1, the variances for group 2, the variances for group 3, the variances between each one of those of the scores between those groups. So we know when we do this calculation, you see where all that's from, but it is sensitive to sample size, so we have to basically get an average of that. All right, so we're going to calculate the mean square error, which is really an average sum of squares. So we have the mean square of the model and the mean square of the residual. The mean square of the residual is simply the error that's left over after we remove the error that is due to between groups factors, or the difference or the variance that's between groups factors from our overall model. So we have the mean square model and the mean square residual, and that's what we're dividing everything out by. So MSM divided by MSR. Right? So those are essentially calculated by taking the sum of squares for each one of those categories and dividing it by the degrees of freedom, and so we end up with the degrees of freedom for the mean square model equals groups minus 1. So if in our smoking example we had 3 groups, right? So we have 2 degrees of freedom for the mean square model part, and then we have a different degree of freedom for the mean square residual, because that's based on the overall sample size, right? So our degrees of freedom there are n minus the number of groups, which is just exactly what you did when you were doing the t-test stuff. Okay? So in reality, I'm just kind of clarifying here that we use the mean squares because it's a more sensitive, it's a more appropriate tool because it's the average sum of squares and it's not sensitive to sample size. Okay? There are some assumptions with this. We have normal distributions. Okay? Within each group, everything needs to be normalized. You can kind of violate this one, but not much. Right? Homogeneity of variance, again, same thing. You can kind of violate it, but there's some adjustments that need to be made, and we'll talk about that in a second. Independent samples, right? And interval level data, which actually interval level data should have been for the t-test as well, but you need that sort of thing. Okay? The good news is that ANOVA is a very robust statistic. In other words, it can withstand violations fairly well. It's most robust when you have a sample size of n equals 20K. That doesn't mean 20,000. It means 20 times the number of groups or the number of measurements that you're going to make. So in our smoking example, we had 3 groups, so our sample size would need to be 60 in order for our ANOVA to be robust to things like homogeneity of variance or normal distributions. it also requires that the group size be equal. Each one of those group sizes be equal. So you couldn't have 25 in one and 21 in another and 30 in another one. That's going to cause a problem with it being able to make an accurate statement about the data itself. So again, we can, with an ANOVA, which is pretty cool, we can violate normal distributions and homogeneity of variance, kinda. I still don't recommend doing it, and it's questionable in the literature as to whether or not it's how interpretable it is when you do that. But that said, there's been quite a bit of research on it that says, yeah, for the most part, if you violate it a little bit, then you're okay. Right? But you cannot violate the independence factor. It's not robust to that. It'll give you a result, but it'll be completely uninterpretable. Okay, so when we get that F score, so remember we're talking about simple ANOVAs here. So when we get that F score, it's going to be one F score for our data set. So think about this. We've got the patch, the pill, and gum. So it's going to say, yes, you're significant. Great, that's wonderful. But where in the world is that significance? We don't know yet. And that's because the F test is an omnibus test. It just tells us that somewhere in our data there is a difference. It doesn't tell us if it's between group 1 and 2, between groups 2 and 3, or between groups 1 and 3. It won't tell us that. So we need to do something ahead of time, or we need to do something to address that. The first thing is something called planned contrasts. Right? Same type of, it helps prevent family-wise error because now we need to compare group 1 to 2, group 2 to 3, and group 1 to 3, right? So, and as we talked about earlier, that's going to create a family-wise error problem. In other words, we're going to inflate our chances of making a type 1. Essentially what happens with planned contrasts is you use this ahead of time to say, hey, we're going to be doing some additional analyses, so we need to make adjustments to the total variation into its individual components. And this allows us to address that family-wise error ahead of time, believe it or not. And it's really complex as to how it does that, and I'm not going to get into it. But in other words, if you have a prediction about where the differences are going to be, if you already believe that the patch is going to be better than the pill for some empirical reason, then you should go ahead and use a planned contrast. Right? So it's only used when you have a prediction. It's something you do ahead of time. But if you didn't have a prediction, you can do something called post hoc comparisons. All right? There's a bunch of different types of post hoc comparisons, but they all essentially do the same thing. It's used when you don't have a prediction and you need to do a Bonferroni correction. In other words, think of it as a bunch of follow-up t-tests. So we've got that ANOVA, which gives us says that there is a difference between your groups, right? Somewhere, doesn't tell us where. So now we need to go dig in there a little further and say, is it between A and B, B and C, or A and C, or you can use the numbers if you will. But that creates our family-wise error problem, right? Because we're going to do all those t-tests now that we're using the ANOVA to not have to do those in the first place. So what we're going to do is we're just going to then take our p-value, and which assume that's 0.05, and now we're going to do 3 t-tests on our post hocs. For our post hocs, all we're going to do this Bonferroni correction is take that p-value and divide it by 3, so our p-value becomes much smaller, like 0.1 something, right, or 0.01 something. So it gets it to be a smaller p-value, which then makes it harder to get significance, or it reduces our chance of making a type 1 error. But when you do that, we end up causing a power problem. In other words, it decreases our chance to detect an effect, assuming one's there, because we have snuck down that requirement for the type 1 error. We've shrunk that, and we did that with these post hoc tests because we didn't want to make a family-wise error, but there was no guarantee that family-wise error was going to happen in the first place. We just have to be prepared for that, and we have to do something to address that. So using the post hoc stuff, it's the way I've always done it. I very rarely do planned contrasts, but it also makes it very difficult to get significance because you have to have a more extreme value on that critical value for those individual follow-up tests. All right, so how do we interpret it? Here's a good example. Let's assume we're looking at the smoking data. We say, okay, an F with 2 and 27 degrees of freedom equals 8.8, which was significant at the 0.05 level. That's how that reads. The 2 and 27 basically says we had 3 groups, that's the 2, and 30 people. 30 people minus 3 is 27, right? So those are our degrees of freedom in parentheses as always. The F statistic itself is 8.8, which supposedly, I didn't look any of this up, this just made up these numbers, which supposedly happens at a p-value of less than 0.05, given those things. Of course, then we would do our we would look at our planned comparisons and also our post hoc tests if we were doing that. And again, post hoc tests and planned comparisons read just like the t-tests do, because essentially they're just a modified type of t-test. All right, let's move on and talk about another type of ANOVA, which is where ANOVA really starts to show its power, and that's in a factorial ANOVA. Okay? In the past, we were just looking at that one factor, right, that one independent variable, but we can actually look at multiple independent variables at the same time. Just don't forget that the ANOVA is an omnibus test, so it's just going to say there's differences, and it's not really going to tell you where. So there's a lot of additional work that has to happen when you do a factorial ANOVA, but it does allow us to look at multiple independent variables at once. Right? So factors equal independent variables, x and y, or y, and all this stuff. So let's look at an example here. It makes it easier. Okay, we're going to, as we look at this example, keep these two things in mind. We're going to look for main effects. There can be a main effect for each, or there can be a main effect of each independent variable and an interaction between those variables. So let's go ahead and look at this next slide here. All right, here we have two factors. One of them is sleep and one of them is teaching style, right? So we're going to say that we're measuring test scores. So the effectiveness of, or how much does the amount of sleep you had the night before affect your test scores, and then also the additional question, how much does teaching style affect test scores? And then a third question is there an interaction between the amount of sleep you've had and test and the style of teaching that was given? So you can look through those, and let's just assume those are all means, 88, 83, 79, reading across style 1 row there. So it looks like it's generally decreasing as you go up in numbers there, sleep 1, 2, 3 conditions, whatever those are. So you can go 8, 4, and 0 sleep or something like that. And then the next one's kind of interesting. In style 2, notice it goes the other direction, 57, 63, and 77. And then in style 3, it's just kind of, it goes even a different direction yet, 45, 49, and 41. So there seems to be something going on there, right? But if you look across the board, as you go up from sleep 1 to sleep 3, then you tend to get an increase in your test score, and as you go from teaching style 1 to teaching style 3, it tends to decrease. But notice that there was those weird little fluctuations in there in terms of the patterns. The patterns for style 1 is sleep 1, sleep 2, sleep 3, it's always decreasing. Style 2 again is increasing across those conditions, and then style 3 is increasing and decreasing. It's kind of just going all over the show. So, all right, so when we do that, now we're going to continue with this analysis, and it's going to spit out a bunch of results. So a factorial ANOVA is going to give us a ton of stuff, right? So it's going to give us, first off, the results of the main effects. This is going to tell us whether or not there was an effect of the amount of sleep you had on test score, and it will tell us whether or not there was an effect of teaching style on test score, right? So in this one-way ANOVA, in the simple ANOVA, we only have one main effect. Now we have multiple possible main effects, right? So again, there's an example that actually doesn't make any sense for this course. I can't believe I pulled that in there. That's hilarious. Anyway, we're just going to ignore that example. Let's continue with the example that I had in there of the sleep and the style. And so just ignore that little subsection there. In fact, I'll just make it disappear. So again, like I was saying, does the amount of sleep affect test scores? And if the answer is yes, you will have a significant main effect for sleep. And then we could ask about teaching style. Does that affect test score independent of sleep? And you say yes, and then you would have what we call a main effect of teaching style as well. Okay? But then we also need to know something else, and that's an interaction, right? So an interaction variable is between teaching style and the amount of sleep. So the interaction reports that the effects of both on the main effect variables of the interaction test reports the effects of both of the main effect variables combined. So was there a differential effect of teaching teaching style depending on how much sleep you had? And the answer could have been yes, right? So that would mean that sure, there was a main effect of teaching, and sure, there was a main effect of the amount of sleep you got, but maybe it was that as you got more sleep, one of those the teaching style that was most effective changed. Right? So instead of always following the same pattern, it could be an interaction between those particular patterns, and that at one level of sleep you get more, the teaching style 3 is more effective. But if you ignore sleep, maybe teaching style 2 is the most effective. But adding in that sleep information can get you some additional stuff. And that's really the power of factorial ANOVAs and these things. So as you can imagine, we're going to get a lot of statistics that are going to spit out. And in fact, for our example, we're going to end up with 3 specifically. And so here we go. We're going to have a main effect of teaching style, so an F with 2 degrees of freedom. and I'm just making all these numbers up. And we're going to say, hey, that's significant at the 0.01 level, right? But so we have a main effect of teaching style, a significant difference of exam score depending on the teaching style, right? That's how we interpret that. But don't forget, there were 3 levels of teaching style, so we don't know where they are yet. So we're going to have where that difference is because this is omnibus. So we're going to need to do those post hocs or the planned comparisons to find out where the difference was in teaching style, which one was the most effective, right? So that's something we haven't answered yet. We just said that, hey, there was a difference. Okay? Now, we also have to look at the main effect of sleep. F of 2 degrees of freedom equals 1.9, P equals 0.18. So it's not significant. The first one was significant because it was less than 0.05. This one is 0.18, so it's not significant. So the main effect of sleep, so sleep did not have an effect on test score. This is completely independent of teaching style though, right? Because it's just looking at it by itself. So now we can look at the interaction and say, all right, an F of 4, right? With an F with 4 degrees of freedom equals 13.5 with a p-value of less than 0.05, so we would say that is significant. In other words, we have an interaction between those two variables here, and they combine to produce their own effect independent of each other's own effect, right? So notice that the main effect of sleep, there was no difference there, but when you put it in, when you have it interact with the teaching style, then it becomes some sort of, it does have some sort of effect there. Okay, so once we've figured out that stuff, we need to ask where those differences are. Was there a difference between between time 1, sleep level 1 and sleep level 2, while taking into account the teaching style, or was there not? You know, that type of thing. So we need to get in there and figure out exactly where those details, where those differences are, and if there are any differences at all. So there may be no difference between teaching styles at, for example, there may be no difference in teaching styles at sleep level 1, maybe no difference at sleep level 2, but there is a difference at sleep level 3. That's an example of a follow-up analysis to find on that interaction. Right? So again, we would use planned contrast, or we could use post hoc tests with the Bonferroni corrections. So that's a very quick summary. There's quite a bit more to it, but that's essentially all we need to know to interpret these statistics if we run into them. All right, talk to you again soon.